The simplex, with its 10 triangular faces. Of course, these two-dimensional faces are pieces of spheres, just as before when we saw that the edges were circular arcs. The simplex is spinning in 4 space, before being projected stereographically. Remember when the Earth was spinning like a ball, and we saw the motion of the continents? Now and again, a face passes through the projection pole, and the projection becomes infinite. It looks like it blows up on the screen. Let's take a quick look at the hypercube. You see that the space is divided into 8 cube-shaped zones. These are the 3-dimensional faces of the hypercube. As for the 2-dimensional faces, they are squares, though rather bloated and twisted. There are 24 of them. My favourite, the 24 cell. Look at that. The 24 cell is really wonderful. 24 vertices, 96 edges, 96 triangles, and 24 octahedra. 8 edges start at each vertex. Here's the 120 cell. Let's try to understand its geometry better. Four edges start at each vertex. The two-dimensional faces are pentagons. There are 720 of them. These 720 pentagons form 120 dodecahedra. Look at all those dodecahedra fitting nicely together. Isn't that amazing? Let's finish with the 600 cell, with its 600 three-dimensional tetrahedral faces, its 1200 triangular faces, its 720 edges, and its 120 vertices. Trust me, there are 14,400 symmetries of force space which preserve this object. Well, there you are, we're done with our first voyage into the fourth dimension. It's a dimension full of amazing things. Of course, the mathematician's imagination isn't limited to the fourth dimension. There are the fifth, the sixth, the nth dimensional, and even the infinite dimension. Each dimension has its own character, but it has to be said that the fourth is the prettiest. Why? Maybe because after all, it has a sort of physical reality. Einstein's relativity theory, dating from the early 20th century, postulates that space and time are somehow bound together into a four-dimensional space-time. A point in this space-time is an event, characterized by its position in space x, y, z, and by the time t when it occurs. Dealing with relativistic physics therefore requires an understanding of four-dimensional geometry. It is interesting to notice that the discovery of this four-dimensional geometry precedes by some 50 years the discovery of relativity. It's one of the many interactions between mathematics and physics that the history of science delights in.